All right, this is a relatively brief model on the optical property of relief. Relief is a measure of the relative difference in the refractive index, which is, we use N to represent the refractive index, between a mineral grain and its surroundings. So this is a property that you see visually, usually best in plane polarized light. And we can also use the relief that we see in a mineral to kind of estimate what the value of N might be for that mineral. So for example, if you look on the left, there's a grain of quartz at the center of that image. And it's hard to see because quartz has a very low relief in that image. And you look on the right, and we have a grain of garnet. It's much easier to see. It has high relief. The edges are clearly defined against whatever the garnet is set into. And the reason that we see that relief is because these grains are mounted in an epoxy that adheres them to the glass slide that they're on. And the refractive index of the epoxy is about the same as quartz. And so there's very little difference in the refractive index, and so it has low relief. The refractive index of the epoxy is much lower than that of garnet. If you look at the values on the right-hand side here, you'll see that epoxy has a refractive index of 1.54, and garnet is about 1.7 to 1.9. So that difference, even though the numbers are small, that amount of difference has a great effect on the kind of relief that you see. Notice that quartz has a refractive index of 1.54 to 1.55. It's very close to the epoxy, and it has a low relief. And you can have higher reliefs, higher indices of refraction for other minerals, or somewhere in between this quartz and this garnet, a whole range. So that value of N, that number, is calculated from the velocity of the light in air divided by the velocity of the light in the mineral. And if the refractive indices are different, the more different they are, the more refraction you're going to get of that light as it passes through that boundary. So the refractive index is also a function of the crystallographic orientation of anisotropic minerals, meaning that depending on how the crystal is oriented in the thin section when it was cut, there can be variability in the refractive index. And so we'll see, if you look up in a reference text, you'll see a range of values for N for different orientations. Isotropic minerals, those are ones like garnet, have a single refractive index because light is passing through at the same speed no matter which direction the crystal is oriented. Uniaxial minerals like quartz have two refractive indices, and biaxial minerals are generally characterized by three refractive indices. So you see a single value for garnet in a reference text, you'll see two values for quartz, and you'll see three for any of the biaxial minerals. And this refractive index gives us a couple of parameters that we can measure, and those are relief and birefringence. So as I said, the relief is the measure of the relative difference in the refractive indices between the mineral and its surroundings. And usually it's not, when we're looking at rocks, we're not looking at a single grain in epoxy, but a grain of one mineral up against a grain of another mineral. So we're comparing relative differences in refractive indices in this image between olivine and plagioclase. And you can see that the plagioclase is much lower relief. It's hard to see the actual individual grains in plain light, and the olivine is very easy to see. You can see fractures running through it and the edges of the grain very clearly. It has a high refractive index, and it has high relief. And we look at the actual values for olivine and plagioclase. You see that plagioclase, again, is very similar to, has a refractive index very close to that of the epoxy that this is mounted in. And the olivine has a much higher refractive index for that mineral compared to the epoxy. So we're looking at differences in the way that the light is refracted through the minerals. And you can have a refractive index that is greater than the epoxy, like we've been seeing with garnet and olivine, or it might be very similar, and that difference with it, the refractive index in the mineral being much higher than the epoxy gives you high relief. If it's about the same as the epoxy, you see low relief because the light is not refracted much or at all. Or the refractive index in the mineral might be much less than the epoxy. So, and that would also give you a high relief, but in a negative relief. Okay, so what you learned here, relief results from differences in the index of refraction, which is denoted by N between minerals. And you'll see those N values listed in reference materials. N is 1.54 for epoxy in your thin sections. So all the values you look up for the minerals are going to be relative, you should consider relative to that value. So any mineral with a refractive index significantly higher or lower than 1.54 will appear as high relief. Any mineral with a refractive index similar to the epoxy, like quartz and feldspars, will appear as low relief. And then there are a whole range of refractive indices that are in between those values that will give you an intermediate kind of relief. Now I'd like you to watch the videos of thin sections 8 and 32 and complete a quiz on relief.